Welcome back to another explainer. Today, we're taking a closer look at a box that sits in almost every single kitchen around the world. We interact with it daily, we rely on it constantly, yet we rarely pause to appreciate the absolute incredible physics happening right inside it. Okay, let's dive into this. The everyday magic of the microwave oven. It's a question that sounds almost absurd when you finally stop taking the appliance for granted. How exactly does a completely cold metal box manage to boil a cup of water in just 60 seconds? I mean, think about it for a second. There's no fire in there. There are no glowing red coils or obvious heat sources. You simply place a mug inside, press a button, it hums, and out comes piping hot liquid. It feels like magic, but it's actually this elegant, everyday scientific mystery just waiting to be unraveled right on your countertop. To truly understand this mystery, we've got to rewind the clock back to the year 1947. This was the year that an engineer named Percy Spencer accidentally discovered the rapid cooking potential of electromagnetic waves. And this brilliant little observation led to the invention of the very first microwave oven. But the coolest part? Percy wasn't working in some kitchen appliance laboratory. Oh no. He was actually working with active radar sets. That's right, the microwave oven was born directly out of World War II radar technology. It is incredibly fascinating to think about that context. Every single time you're just casually popping a bag of popcorn for movie night or reheating your morning coffee, you are literally utilizing weapons-grade physics. You are harnessing the exact same electromagnetic principles that militaries use to detect enemy aircraft. Now let's clear up a major myth right off the bat before we get into the mechanics. When people hear the word radiation, well, they tend to panic. But the microwaves used here, which operate at specific frequencies between 300 megahertz and 300 gigahertz, are strictly non-ionizing radiation. I really want to emphasize that word, non-ionizing. This means they do not have anywhere near enough energy to alter the chemical structure of your food or make it radioactive. They simply and safely pass right through materials like glass and plastic, zeroing in exclusively on the food itself. So, the crucial point is this core concept, dielectric heating. This is the absolute star of the show. Dielectric heating is the process where electromagnetic waves excite polar molecules, mostly water, generating heat directly from inside the food. Unlike a traditional oven that slowly pushes heat from the outside air into your meal, microwaves bypass the air entirely. The air in the microwave stays cool while the food gets piping hot. But how exactly does exciting a molecule make it physically hot? Well, microwaves cause these polar molecules, your water, your fats, your sugars, to flip, vibrate, and rotate incredibly fast. I want you to imagine stepping outside on a freezing winter day and rapidly rubbing your bare hands together to warm them up. That mechanical friction generates heat, right? That is exactly what billions of microscopic water molecules are doing inside your leftover pizza. They rub against each other, creating intense molecular friction, and that friction is what actually cooks your food. Let's virtually open up the box and look at the anatomy that makes this incredible process happen. There are four main components you need to know, and they all work together in perfect harmony. First and foremost is the magnetron. This is the absolute heart of the microwave. It takes normal household electrical energy and converts it into those high-frequency electromagnetic waves. Then we have the waveguide, a channel which literally directs those waves into the cooking chamber. That chamber is a metallic box meticulously designed to bounce and reflect the microwaves around without letting them escape. Finally, the turntable keeps the food moving so the waves hit it from all possible angles. When you hit that start button, this sequence fires off blazingly fast. Let's step through it to see how it all connects. Step 1. The power supply rushes electricity in. Step 2. The magnetron instantly activates, churning out those microwaves. Step 3. Wave transmission, where the waveguide blasts these waves straight into the chamber. Step 4. Molecular interaction begins as the water molecules in your food absorb the waves and start violently vibrating. Step 5. Heat generation peaks through that intense friction. And Step 6. The turntable spins everything for uniform cooking. Boom, a perfectly reheated meal in mere seconds. However, this incredible speed does come with a specific scientific limitation, and that limitation is represented perfectly by the number 2.5. You see, microwaves only have a penetration depth of roughly 2.5 centimeters. That's about an inch. They don't magically reach the absolute dead center of a massive frozen turkey right away. The waves hit the outer 2.5 centimeters, heat the water there, and then that heat has to slowly conduct inward to the rest of the food naturally. This is exactly why thick foods can sometimes heat so wildly unevenly, leaving you with a boiling hot outside and a stubbornly frozen center. This brings us to a really helpful comparison. When we look at a microwave versus a conventional oven, we're essentially comparing molecular heating against external heating. The microwave is very fast, highly energy efficient, and great at retaining the moisture inside your food. But because the surrounding air in a microwave stays completely cool, remember the waves only target the water molecules, it has very poor browning capabilities. You simply aren't going to get that delicious, crispy skin on a roasted chicken or a crusty baked bread like you would in the slow, dry heat of a conventional oven.
Now, what's really interesting about this slide is that this technology isn't just confined to your kitchen counter. The exact same dielectric heating principles are heavily utilized in massive industrial applications. We're talking rapidly drying tons of wood and textiles, or curing industrial glue on huge assembly lines. In the medical field, it's used for high-level sterilization, and even in physiotherapy for deep tissue heating, a treatment known as diathermy. Laboratories use it constantly for safely and efficiently drying chemical samples. It is an absolute powerhouse of an invention.
Of course, operating a miniature radar box inside your house does come with some essential, non-negotiable safety rules. Never use metal containers, avoid sealed containers, and absolutely never run the machine while it's empty. If you forget to poke holes in that sealed plastic container of soup before hitting start, the rapidly expanding steam trapped inside will violently turn your lunch into an explosive modern art piece, decorating the entire inside of the cooking chamber. And trust me, nobody wants to clean that up. And what about that cardinal kitchen rule? Absolutely no metal? Well, this ties perfectly back to the physics we just talked about. The cooking chamber itself is made of metal specifically to bounce and reflect the microwaves. So, if you put a metal fork or a crumpled aluminum tray in there, the microwaves violently bounce off those objects too. This creates an intense buildup of electrical charge on the metal surface, which inevitably discharges into the air. The result? Terrifying sparks, arc flashes, and potential ruin for your beloved magnetron. Keep the metal out. And this brilliantly illustrates why this topic is so worthwhile to explore. As our source material points out, the microwave oven is so much more than just a convenient appliance for reheating leftovers. It perfectly demonstrates key fundamental concepts of electromagnetism, molecular motion, and energy conversion, all sitting right there quietly on your countertop. It's basically a daily interactive physics lesson, taking electrical energy straight from your wall and efficiently transforming it into heat right inside your food. As we wrap up this explainer, I want to leave you with this final, kind of provocative thought. Did you know that your food continues to cook even after the microwave timer dings and the machine shuts completely off? Because the microwaves only penetrated that outer 2.5 centimeter layer, that intense heat continues traveling inward through conduction, while the food just sits there resting. That's why those "let's stand for 2 minutes" instructions on frozen meals are actually a crucial part of the cooking process, not just a polite suggestion to avoid burning your tongue. Next time you punch in those numbers and watch the turntable spin, ask yourself, what other invisible magic is happening around us every single day? Thank you for tuning in, and keep on learning.